All right, everyone, welcome to this video on isotopes and isotopic abundance. So I have here, I've got a picture of some elements. I want you to try to identify them. So pause the video, see if you can figure out what they are. So pause right now. Okay, let's see how we did. So what you want to do, remember, is you want to look at the number of subatomic particles. Let's look at what we have here. So here I'm going to have 1, 2, 3, 4, 5, 6. So I have 6 of these protons. All right. And then inside here I also have some neutrons. Looks like I've got 6 neutrons in the nucleus. And let's see what's happening around here. Looks like we have 2, 4, 6, 6 electrons. So it looks like we have here, it's a neutral atom, so it's neutral. And when you look at the periodic table for 6 protons, that's an atomic number of 6, that is going to be carbons. We have here carbon. Now, on this side over here, what we have is we have something similar. We've got 1, 2, 3, 4, 5, 6, 6 protons. Here, when you count the neutrons, you have an extra neutron compared to before. We have 7 neutrons, but the electrons are the same. So the electrons are still 6. So that means we have 6 positives, 6 negatives. We have a neutral atom, and it's still carbon, but it's a little bit heavier. So this is an isotope of carbons. When you have different numbers of neutrons, you have isotopes. So both these are carbon. I have to call them something, so we call them according to the number of entities they have inside the nucleus. So here I've got 12 things in the nucleus. It's going to be carbon 12. Here I've got 13. This is going to be carbon 13. Let's look at the last situation here. So again, here we've got 6 protons. And we have here 8 neutrons. So you have even 2 more than the original. The electrons are still the same. So we're still neutral. Nothing fancy happened there. So we have a neutral atom of, but this time it's carbon, but now it's going to be carbon 14. We have 14 entities in the nucleus. And that's kind of the idea behind isotopes. So let's look at another example here. Here we've got hydrogen, and this is from your note. So you have hydrogen 1, hydrogen 2, hydrogen 3, and what is the same here? You have the same number of protons. The protons determine who you are. So if you have 1 proton, you're going to be hydrogen. But what happens is the number of neutrons varies. Here I've got 0, here I've got 1, here I've got 2 neutrons. So the number of neutrons will vary. And this is going to influence the atomic mass. So the atomic mass is going to change, or varies. However, remember, because you have the same number of protons, the atomic number is constant. It doesn't change. Okay, so it's constant. And that's kind of the idea behind isotopes. Again, same thing as before. So what I have here, I've got isotopes of magnesium. So I've got 3 possible isotopes. We can have magnesium. Here it has a mass number of 24, so we call this magnesium 24. Here we've got magnesium 25, again has an extra neutron. Here this is magnesium 26, it has extra 2 neutrons compared to before. And when you look at this, and let's look at the periodic table, when you look at the atomic mass for magnesium, it's 24.31. So 24.31. Why is that? Well, you have each of these isotopes found in nature. And depending on the proportion of them, you're going to have a different percentage of them. And that's going to determine this average. This is an average mass that we have over here. And because it's 24.31, it's likely that this is the most common isotope. It'd be magnesium 24 because we're closer to magnesium 24 than any of the other atomic masses. And that's kind of the idea behind this. And in fact, the proportion is 78.99% of magnesium 24. And the other 2 are found in lesser amounts. So this is common for most of the elements in the periodic table. The proportion is going to be different. Some of them have very few isotopes. Some have numerous isotopes. Some have numerous, but there's one predominant one. So again, it varies. It really is distinctive for each element. And remember, these are, when you look at the proportion, this is the estimated proportion that's found in nature. So depending on what country or what scientific advisory body, you might have some differences in these quantities. So let's look at this one here. We've got iron. Now, iron can have several isotopes. It can have 54, iron 56, 57, and 58. Now you look at the periodic table, the average mass is 55.85. So it looks like it's most likely going to have a lot of iron 56. Let's look at the graph over here. So the graph over here, you can see that the majority here is in fact iron 56 with smaller amounts of the remaining isotopes. Now what we want to do is we want to actually calculate the exact amounts or calculate the average atomic mass, and that's what we're going to be doing in the rest of this lesson. So what we want to do is let's look at how we can actually look at, let's say, an example of your marks. Let's say that you're taking a course, and then in your course, you're going to have two tests. So we'll call this test 1, and this will be called test 2. And each of them is worth 25% of your mark. Okay? Please look up pie graph over here, pie chart. Then we have an exam, and the exam is worth 50% of your mark. And this is very typical what you have in a lot of post-secondary courses. You have a few tests and just one exam. The exams being the majority of your mark. So you always want to do well in the final exam. So let's say that on your first test you had a 72%. And the second test, a little bit better, you studied a little bit more, you had 80%. But then on your exam, you had a lot of trouble and you only ended up getting 60%. So how would you calculate your average mark? Well, let's figure that out. So the average mark, what you do is this. You take the percentage of each assessment. So let's look at the exam first. It's 50%. I'm going to write it down as a decimal. And my mark here was 60. And then I'm going to add that to how well I did on each of the tests. So the first test was worth 25%, and I had a mark of 72. And then I had another test, also 25%. And remember, this one I had an 80 on it. So what we do is you take the proportion times the actual mark. So here would be 30. 25 times 72, I think that's 18. And a quarter of 80, well, we know that. That's going to be 20. And you add all of these up, 30, 40, 50, your final mark would be 68%. And this process is very similar to how you find the proportion of isotopes in nature and how you determine the average atomic mass. So let's look at an example. So here, what we're going to do is use the same process. So we'll be looking for the average atomic mass. Okay. So average atomic mass. And here's what we know. For this element here, we're going to have chlorine. And chlorine has two main isotopes. It has chlorine 35 and 37. So 35 chlorine is 75.77% in nature. So let's write that down as a decimal place. 77, put the decimal place over here. And the atomic mass is 34.969 U. This is called an atomic mass unit. Now remember, atoms are so tiny, I can't use grams to find their mass. So we use something called the atomic mass unit, AMU, and the actual symbol is just called U. So next thing we want to do is we want to determine the last component here. What proportion of chlorine is 37? What's the contribution in terms of the mass? So this would be 0.2423%. And the mass of chlorine 37 would be 36.966 atomic mass units. So we do a little bit of math and see what we get here. So multiply these through, and I end up with 496 U. And this one over here, I'm going to multiply these through here, 8.957 U's. And we add these together, and what do we end up with? 35.45 U's, atomic mass units. So on average, in nature, the mass of chlorine is 35.45 because some of it's contributed from mass of chlorine 35 and some of it's contributed from the mass of chlorine 37. How does that compare to the periodic table? Let's look up chlorine. Oh, look at that, 35.45. There we go. So that's where these numbers come from on the periodic table. If you're ever wondering, there we go. Let's do another example here. This one, I want you to try it, and then you're going to pause the video. We start the same way. I'm going to write this down. Average atomic mass. And you're going to do this. You're going to multiply the percentage times the actual mass of each of these isotopes. You have 3 of them here. And your final answer should be 24.31. So pause the video, actually do this on your calculator. It won't take very long. Okay, now that you've paused, let's see how we did. So again, what we want to do is you take the percentage, so here, 78.70, change it into a decimal, and you multiply it by the mass for that particular isotope. So here, magnesium 24 is a mass of 23.985. And then same thing over here. Here's my percentage. Here's the mass of magnesium 25. And lastly over here, I have my third isotope. There's my percentage. There's the mass of magnesium 26. You multiply through, find the sum, and you end up with 24.31 atomic mass units. That's the average mass of chlorine in nature. And when we, magnesium in nature. And we look at magnesium, here you go. Oh, look, it does match. The atomic mass is 24.31. So you can see that the majority of the magnesium in nature is because of this magnesium 24. So these are actual values. And what you do is normally you'd measure this in lab. You'd take different samples and you find an average proportion of the magnesium in each, and then you make a little bit of an estimate. All right? Okay, so now we're going to be doing something different. I want to determine what is the percentage. I don't know what the percentage is of potassium. So potassium, we have 2 isotopes. We have potassium 39 and potassium 41. And I don't know which one's which in terms of the proportions. Which one has a higher percentage? What I do know is that the average mass in nature is 39.10 atomic mass units. You have a little U there. So it's likely that we're going to have mostly potassium 39. But how much actually? So here's what we're going to do. We're going to do a little pie chart here like we did for the marks. So we know that most of our potassium is going to be potassium 39. And we're going to have a little bit of this potassium 41, just like that. Now, I have to determine the percentage of each of these. So I'm going to do a little shortcut. I'm going to show you a quick way of doing this. Now, this is not related to the question, but it's going to help you understand what we're going to be doing in terms of the framework of the question, how we go through it. So let's say I had a situation where I had 2 isotopes. Again, it's not related to this question. I'm making up numbers here. So let's say I had 74% of one isotope. I want to know what percentage is in the other isotope. And you say, hey, that's easy. What you do is in your head, you say, oh, it's easy. 100 minus 74 gives me 26%, right? You can also do it mathematically, though. So you can go like this and say, okay, I've got 0.74, so 74% of this isotope here, and this is going to be X, right? And what you can do is say, okay, I know that 1 plus X has to equal, or sorry, 0.74. Sorry, that's what I meant. Plus X is equal to 1. What's X equal to? 0.26. So we're going to use a strategy something like this. However, it's going to be even cooler than that, because look what I can do as well. I can also do this. I can say, okay, if this is going to be X, this is going to be 1 minus X. Right? So 100 minus X. And I'm going to use this system over here to figure out what my proportion of each isotope is. So this is going to be my percentage of the isotope potassium 39. And this X, just on its own, is going to be the percentage of potassium 41. Let's do a quick question with this. So I'm going to just erase everything I have here. So what we do is this. I'll say, okay, let's make, it really doesn't matter here, but let's make the percentage of potassium 39 equal 1 minus X. And the percentage of 41, potassium 41, that's going to be X. Remember my little circle here. right? So here we go. Sorry, this is 41 potassium, 39 potassium, 1 minus X, and this is going to be X. So what we can do is we can actually solve. Let's see how we do that. So over here, I'd have, okay, so for the average atomic mass, I know it would equal to the percentage of potassium 39 times the actual mass of it, which happens to be here, 39.01 atomic mass units. And the percentage of this would be equal, multiplied by 41.01 mass units, just like we did before. The only difference is instead of finding the average mass, I know the average mass. From the periodic table, I know it's going to be 39.10. And remember this percentage of potassium 39? I'm going to put in 1 minus X over here times 39.01U. And this percentage of potassium 41 is just X. So you're going to have X and 41.01 atomic mass units. So what we're going to do is we're going to solve for X, and that's going to tell me how much of this potassium 41 that I have. So it's just a basic matter of going through here with math. So I have 39.10. Here you have to be careful, you have to use distributive properties. So we're going to have 39.01 atomic mass units minus 39.01 X, UX, we'll call that. Don't forget about that. Plus 41.01 UX. So what we have to do is we have to find the common terms associated with all of these, right? So what we want to do is we're going to multiply through, we've done that, and now we're going to collect the like terms. So I'm going to bring these over. So this 39.10, and I'm going to subtract 39.01, so be careful with that. So 39.10 minus 39.01, what do I get here? 0.09U. And what do I do on this side? I collect the like terms here. This is going to be the X. So here I'm going to have 39.01 subtracted from 41.01, so it's going to be just 2UX. And what happens is these units cancel, right? And we divide now, 0.09 divided by 2. So 0.09 divided by 2 gives us 0.045 is equal to X. Now, this is my decimal percentage. So to get the actual percentage, we multiply by 100%. So therefore, the percentage, remember what X was. X was equal to the percentage of potassium 41. So the percentage of potassium 41 is equal to 4.5%. But wait a second, how about the percentage of potassium 39? Well, the percentage of potassium 39, sorry about that, is going to be equal to 1 minus X. Well, what is it? 1 minus, we know X is 0.045. And you do a little bit of subtraction here. Here we go, get the calculator out. And we end up with 0.955. So the percentage, bring this up a little bit, the percentage of potassium 39 is going to be 95.5%. There you go. And it makes sense because remember, the average value is around 39. So it should be mostly 39 potassium. And just a little bit of potassium 41 in it. And you want to just double check and make sure that these two add up to 100%. And that's it. So this is a complicated question, but it's not too bad if you set it up properly at the beginning. Okay? Online, you're going to have a nicer version of it. It looks like this. It's a little bit cleaned up, but it works out exactly the same. So that's it for isotopic abundance and percent isotope relative amounts in nature. Take care.